Okay, let's try to do an example of a surface integral that would be relevant to the integral theorems, okay, especially the Stokes theorem. Well, first we're going to do one where we just get a surface area. Then we'll do the dot product of a curl with a normal vector or something like that. Okay, surface integral. We parameterize a surface. Now we already have given as an example where x equals v cosine u, y equals v sine u. Since then, x squared plus y squared equals v squared. This gives us a circle of radius v as u goes from 0 to 2 pi. And if we let z equal 2v, that's pretty simple. We get a cone, okay, with the apex at the origin and so forth. So let's just use that parameterization and let's be real explicit. Let's let x equal v cosine u, y equal v sine u, z equals, I think I used 2v here, so it's going to be a cone with slope, loosely speaking, of 2. And then 0 less than or equal to u less than 2 pi. And let's just say 0 less than or less than or equal to v less than or equal to. So v goes up to 3, meaning your circle is going to have any radius from 0 to 3. So you're going to have circles in the xy plane of radius all the way from 0 to 3, because v, of course, is the radius of the circle you get, and v runs from 0 to 3. And of course, u goes from 0 to 2 pi, so the cosine and the sine generate the whole circle. I think we pretty thoroughly understand that. And then v goes from 0 to 3. So you're going to have circles out to radius 3, and v is going to go from 0 to 3, so that z goes from 0 to 6. So this cone is going to be 6 units high. It's going to have a slope 2 with respect to any of the coordinate planes, or within any of the coordinate planes, slope of magnitude 2, if you wish. So we can pretty easily visualize this surface. Okay, well, of course, our parameterization will then be this, okay? X of u, v, y of u, v, z of u, v. Here they are. So r of u, v equals v cosine u times I plus v sine u times j plus z, which is 2v times k. Okay, now that's a relatively easy surface to parameterize, but if you can parameterize that, gives you a basis for parameterizing things that might be a little more complicated. So what do we do now? Well, first of all, I didn't mention this in the summary, but my UV rectangle goes from 0 to 2 pi in the u direction, and from 0 to 3 in the v direction. It's a rectangle in the UV plane. Now, the UV plane is a parameter space. It has nothing directly to do with the three-dimensional space that we're modeling the cone in. It has actually nothing directly to do with the cone. But when we partition U and partition V, we get delta U by delta P rectangles. I'm not going to do a thorough explanation of this. I'm not going to do that explanation at all. If I can't find my red chalk, where the heck is it? There we go. Okay. So here, let's just say this is our typical delta UI by delta VJ. rectangle with sample point UI star VJ star. Then this rectangle maps onto our cone. Now our cone is here. We go up to altitude 6. So here's z equals 6. In the XY plane, we go out to a circle of radius 3. Okay, not all that well drawn, and my z scale is all screwed up now. And we have, circles concentric all the way out. And for every circle, we come up 2V units. So that what we end up with, and hopefully you've done examples of this nature, is we can kind of do an auxiliary XY set of axes up here at z equals 6, and we draw this outer circle. And then our cone just tapers down to the origin. Now that's kind of poorly drawn, I guess, but from the side, we have Z, and we have any line in the XY plane, and the thing actually looks like this. And it is a solid rotation of this shape. So we have our circle of radius 6 up here. No, I'm sorry, it's not radius 6, but the height is 6 units, and the radius is 3 units. And I'm not going to label the z-axis. Yeah, maybe I could just move on to z. Okay. Now on this surface, well, the UV parameters here are going to map, your sample point is going to map to a point on the surface. And this rectangle here in UV is going to map to a delta X and a delta Y, and is going to ultimately then map to, and we should have drawn this a little better, but if we now think, okay, let's go ahead and rotate this. So now here's a picture of our cone. It's going to map to some part of this surface. Now, this part of the surface is going to have what dimensions? This maps to a delta X I'm just going to say a delta X by delta Y. I'll try to make that a little clearer. This rectangle will map onto this surface to the point X of UI star VJ star. So remember, there's our X of UV, our Y of UV, our Z of UV, right? So we're going to have a point here, which is going to be X of UI star VJ star. Y of UI VJ star Z of UI star VJ star. That's the image of our sample point in UV parameter space. So this rectangle maps to a region here that is defined by two tangent vectors. The tangent vectors are RU, the derivative of R with respect to U, where R is this, evaluated at UI star VJ star by RV of UI star VJ star. Now, this is not a multiplication, these are dimensions. Because RU and RV cannot be considered to be mutually perpendicular. RU and RV are tangent to the actual surface here. The area, okay, this is a parallelogram. The area of the parallelogram is cross product of the two vectors that define it. And you go back to when we first studied cross product and make sure you understand the area of a parallelogram, the triple product, the volume of a parallelepiped, and so forth. I'm not going to go over all the details of that. I'm going to assume that. Okay, so we have this point based on the sample point in this one IJ rectangle in UV space. Areas RU by RV. Okay, so the area increment another, and when I say the area is this, I mean area is the magnitude of this. RU cross RV is a vector. And that was sketched. We sketched it schematically right here. Here's our RU, delta U, and our RV, delta V. And shucks, I left something out here. Got to fix it. I'm going to smudge a little bit. It doesn't have to live with it. Okay. This is a RU UI star VJ star, perfectly good vector. We got to multiply that by delta UI to get tangent vector. And the RV by delta VJ. Okay, this is what's going on. Calculation, your area increment is then this, where RU and RV are evaluated at your sample point. With a normal vector times your surface area increment, approximately equal to RU plus RV, delta U, delta V. Okay, the magnitude of this vector is going to be the area, which is the magnitude of RU, RV, delta U, delta V. And the vector RU cross RV, since RU and RV are tangent to our surface, is going to be RU cross RV, RU delta U cross RV delta V. Okay, now, so far I'm just saying the same thing I said before. But now, what are the details of this? Well, X is V cosine U, Y is V cosine, V sine U, and Z is 2V. So RU, I guess I'm going to just calculate RU in general is the U derivative of X times I plus the U derivative of Y times J plus the U derivative of Z times K vector. And XU is negative V sine U. Plus V cosine U J plus, actually not plus 2K, this is U derivative. U derivative of Z is, well, Z is 2V. Okay, so derivative of this, in other words, with respect to U is what I've written out here. RV is XVI plus YVJ plus ZVK, which you probably don't need me to write out, but just in case. Okay, and XV is just cosine U. YV is just sine U. And ZV is just 2. And the derivative of 2V with respect to D is just 2. Okay, so now I can write. Your area increment, just the area, is R magnitude of RU cross RV delta U delta V. And if this is on the ith interval, or IJ increment of your partition of your parameter space, get my symbols in the right order. The sum of your AIJs approaches your interval. It approaches the integral of magnitude of RU cross RV du dv, where U goes from 0 to 2 pi because that's what our parameter limits are, and V goes from 0 to 3. Your normal your normal times delta SI vector, and that's the normal vector. It's a vector perpendicular to this area increment on the cone, kind of down in this direction. So it's that direction, and it has magnitude equal to the area. So if you're trying to do a flux, you would do the dot product of whatever vector field you're calculating the flux for, bad sense, so be it. So you do F dot this it'll give you the contribution of flux of the vector field F in this direction. So detail. That would be the full vector RU cross RV. Delta UI, delta VJ. And then, well, I'm going to leave it at that for right now because I haven't introduced notation for your vector field. We'll throw in a vector field here using notation similar to what I have here, but let's not complicate it at the moment. So we have this. Okay, well, now we want to look at how we get the actual integral using this magnitude. Okay, limits in the integral are pretty straightforward. We've just got to calculate RU cross RV and take its absolute value or its magnitude. Okay, now let's actually construct this integral and see if we can integrate it. Okay, RU cross RV. Well, here's RU, here's RV. Now I'm going to do the cross product. I'm not going to write out the determinant. It takes too much room. I'm going to use the distributive law. Okay, I've got negative V sine UI dotted with cosine UI. That's going to give us 0 because I cross I is 0. With sine uj, well, that's going to give me minus V sine squared U times I cross J. I cross J is K. So I have a piece of chalk with a hard place on it. Okay, negative V squared sine squared U, K. And then I have negative V sine U I cross 2K. That's going to be negative 2V sine U. And I cross K is J, negative J. So that's going to be negative 2V sine U K. And that takes care of the I component here, crossed with all three components of this vector. V cosine U J crossed with cosine U I. Well, J cross I is negative K, better be negative. So we get, now just a minute, I had a V squared there, but there's no V down here. So when we multiply negative V sine U by sine U, we just get negative V sine squared. We got an extra square in there. Okay, that was starting to bother me because we have to kind of match up here. And this is going to be sine squared. Okay. Then we have V cosine UJ crossed with sine UJ, but you know, J. Wait a minute, am I doing this right? We're doing this crossed with this, which will give me a cosine squared U. I'm sorry, it's late in the day. It's the best I can do. And then this crossed with 2K. J cross K is I. And what happened? I'm leaving stuff off. I need to stop explaining this and just calculate it. And I'll explain where it came from. I want to do these in order. Okay, so this crossed with this, I cross K is negative J, so it's negative 2V sine UJ Then this cross with this, we get a b cosine squared u times negative k, because j cross I is negative k. And then j cross k is I, so we're going to get a plus 2v cosine u I. I'm a little disturbed by a negative here and a positive here. And there's good reason for that. Negative p sine u I. That gives a negative there because I cross k is negative j. And j cross k is I cross k is negative j. Okay, I'm going to take what I've got. Okay, there's my RU cross RV. And that simplifies to negative v k, because I've got a negative v sine squared u, a negative v cosine squared u. We're going to get a negative v k times a sine squared u plus a cosine squared u, which is 1. So by the Pythagorean identity, this is all we get. Then it's going to be plus 2v times cosine u I minus sine u j. And that's going to be our normal vector. I might have been better off doing RV cross RU to get the outward normal, and we'll worry about orientation later. But you see that your outward normal from this is going to have a negative k. This is the outward normal. I don't know what I'm doing. Okay, so we get negative k. And then we have a cosine u I times v, of course, and v is not a vector. So it's going to be a cosine u I. Why do we have a minus sine u j? That doesn't make sense. I think it should be plus sine u j, because in the first quadrant, everything is positive and everything would be down this way and out this way in the positive x and y directions. This is the xy plane, xyz. Okay. So I'm still real skeptical about that negative. Maybe I should have written out the determinant. I don't know. You can work that out, but here's how it comes out in the integral. Okay. Well, the integral for the surface area is just, well, let's do the magnitude. We're going to need the magnitude of RU cross RV. Now the plus and minus signs don't make any difference here. That's going to be, writing it all out, the square root of v squared plus 2v cosine u quantity squared. We're going to have a Pythagorean identity, but let's just go ahead and write out all the details. Okay, there's our I, j, and k components all squared. And this equals square root of 3 times v. Skipping a couple of steps, you factor, you get the cosine squared here, the sine squared here. You're going to get a 4v squared out of both of these. And it's not square root of 3, it's the square root of 5. Times v. You're going to get a 4v squared here, 4v squared here, cosine squared, sine squared. Factor that out, you get 1. Yeah. Here you go, the square root of 5v. I can digress and double check that that makes sense in terms of the slope. I'll just pose the question now, we might come back to it. If my slope here is 2, then is the length of this thing equal to the square root of 2 times the length of this? Is this equal to square root of 2 times this? Well, by the Pythagorean theorem, it's pretty easy to see. It is. For every unit here, you got 2 units here, which means you got square root of 5 units here. So that makes perfect sense. Whether you can reconcile that or not, there it is. We'll probably come back to it. Okay. Now, this makes this integral really easy, doesn't it? Okay. Total area of this cone is the interval from 0 to 3, the interval from 0 to 2 pi, square root of 5b du dv. So that's a really easy integral. Square root of 5 comes out of the integral. You're going to get a 2 pi from the du because there's no u here. And you're going to get a v squared over 2, v squared being 9/2 here and 0 here. You're going to get, and you can work this out. You get 9 times the square root of 5 pi, I think. Total area of this cone. Now, a little geometry. Take this cone and slice it anywhere, just from the vertex up to the upper edge, and lay it out, you get a sector of a circle. Slice the cone, spread it out, you get a sector of a circle. So you can figure out what this central angle here ought to be by the slope. You know that the radius here is going to be 3. So if you just figure out this angle, you can see what portion of a full circle you've got, and you can calculate the area. The area of your circle would be 9 pi. Which tells me that maybe there's something wrong there. And that's because the side is not the square root of 3. This side goes out to 3 here and up to 6 here. So the length of this is going to be the square root of 3 squared plus 6 squared. I told you it's getting late. Okay, which is square root of 42. That's our square root of 45. And pi times the square root of 45 sorry, pi times 45. The area of the whole circle would be the square root of 45. Okay, and the square root of 45 is be 2 pi, 2 times the square root of 45 pi. It's going to be bigger than this, and you'll be able to figure out the proportion. That's an exercise you ought to do, just so you understand a little bit more than you probably do about the area of a surface of a cone. Okay. Another way of saying that is we could have done this in the first place. All we wanted was the area of that cone. But this is to illustrate and show how this whole review gives you the area of the surface. And we are using S for the area of the surface. We'll call that S. Okay, well, that's all well and good. Now, what if we want to calculate a flux of a vector field? Okay, so if f of x, y, z equals f of x, little f of x, y, z, I, plus little g of x, y, z, j, plus little h of x, y, z, k, which is the notation that we used here. Well, since x, y, and z parameterized with the surface are functions of u and v that we see here, we can express this as f of x of uv y of uv z of uv I plus, well, it'd be g of x of uv etc. If we write that out in terms of our uv function, and I'm not sure it's totally necessary to do that, but yeah, I think it kind of is. No, it probably isn't. Depending on what little f, little g, and little h are, we can cut through the chase here by just saying that if we know these three functions, then we can plug in the uv expressions for x, y, and z. And this reduces, and I'm getting into rotational nightmare here, and I do apologize. I'm going to pause the video for a second and think through the notation, or abandon it altogether. Okay, I thought through my notation and realized it's really kind of stupid to be even trying to follow this notation. Let me write it out for a given f of x, y, z and show you how it works, or I haven't been showing you a bunch of complicated and unnecessarily complicated notation. Probably unnecessarily complicated. Let's say, whoops, that okay. And now I got a hard place in chalk. I'll get this written eventually. Let's just make it interesting. Let f be gradient of function x squared y z cubed. I don't really trust myself to do this correctly, but we're going to get x, 2x, see, I almost messed it up, y, z cubed I, plus x squared z cubed j, plus 3x squared y z squared. Okay. Okay, now on our surface, well, let's just get definition of our surface, the parameterization here. And I just move this over a little further, try not to drop the chalk. I'm sorry, it's late in the day. After the last class of the semester. And I'm really kind of okay. But okay, well, let's just see. Okay, on our surface, x is u cosine v, y is u sine v, z is 2v, because we're still on this conical surface. F equals what? Well, it's 2xy z cubed. Okay, well, each x and y gives us a v squared, so we're going to get a 2v squared. Except now we're going to get a v to the third when we do z cubed. So we're going to have 2 z to the fifth. That takes care of our z's. Okay, then x and y each contribute, well, x contributes a cosine, y contributes a sine of u. And there we have it. Okay, x squared z cubed. Well, x squared is going to contribute a v squared, z cubed is going to contribute a v cubed. And oh boy, let's see, I had z cubed here. There's a factor of 8 there because of the 2, so that gives us 16 here. I'll make another mistake, but you'll get the idea. Okay, 16z to the fifth. Okay, x squared is going to be a v squared cosine squared u, and that's going to be an 8v cubed. So that's going to be an 8v to the fifth. That's a cosine of u because it's x. Clerical skills are abandoning me faster than my judgment about how much notation to use. Okay. That's a z cubed, so it's going to be an 8 v cubed times a v squared cosine squared u. That's 8v to the fifth. Cosine squared u times j plus 3x squared y z squared. Each x, each y, and each z is going to contribute a v because v is a common factor. We're going to have a z squared, which is going to give us a 4 here, times a 3, that gives us 12. Z to the fifth. And then we're going to have a cosine squared u from the x and a sine u. And that's not times j, that's times k. Okay. Perfectly good function, not all that complicated. I mean, here it is in terms of x, y, and z. Here it is on our surface, parameterized in terms of uv within this uv parameter space. Now we want to do the integral. Using capital Phi for flux. It's a double integral of f dot nds. Remember, nds is what we had over here. It didn't do too much with, well, we had it somewhere. Wasn't there, it was here. We called it N delta A. I'll change that to delta capital S because we use capital S for surface area. one of the traditional notations. So our N delta SI was this, right? It's RU cross RV delta UI delta VJ. So we might still have a lot of that visible. We've got to pull this over. F is this. E to the fifth, not B squared. Just having copied this down, times our N ds, which is like our N delta S, I guess back here. That we built previously. And that's our RU cross RV, delta U, delta V. So put a big dot here. Then it's times what? RU cross RV. We did that somewhere, like right here. There's a magnitude of RU cross RV, but here's RU cross RV. That's negative V, okay, plus 2V cosine U I minus sine UJ. And then that's times our increment of partition of delta UI delta VJ, but that's just going to be a du dv. Integrating first with respect to u, which goes from 0 to 2 pi as before, and v, which goes from 0 to 3 as before. Would have been better if I'd have put the k on the end here, because then I could have matched it up visually a little better, but be careful. You see this is going to be the interval from 0 to 3 and the interval from 0 to 2 pi. Oh, I component dot of I component. Another factor of 2v cosine u. So we get 32. I wrote z to the fifth there, it's v to the fifth. And here it should have been v to the fifth. Understand how that was done. Okay, so again, we're multiplying this. We get 32. The I dot I component is going to give us a cosine squared. It already gave us the factor of 2 and another v. So v to the 6 cosine squared u plus j dot j. All the j component here adds, well, there's a 2v and then distribute. Okay. Over here, wherever I had it, I don't have it anymore. But I had the 2v times quantity cosine ui minus sine u j, and I didn't distribute properly on this term. So we go back and just look back and see what that is. So again, bookkeeping, I got 8 times 2, which is 16. It's minus 16. I don't think it should be minus, but there's something going on. Minus 16, e to the fifth, and b gives you b to the sixth. Okay. And then times the sine u cosine squared u. And then it's plus your k. Out it with your k. You just have a negative b here, so you're just going to get a negative So I guess I should be careful about my sign. Minus 12 g to the sixth cosine squared u sine u dv. I was hoping something would simplify there, but it doesn't really. And in any case, this is a simple enough integral. The actual answer is going to make a lot of sense, and I think I've got a mistake in there. Yeah, maybe. Because the negative and the negative. Okay, I don't want to think that hard right now. I probably can't think that hard right now, and don't want to do it on screen anyway. Because the side of me beating my head against the wall might be distracting. This illustrates the entire process that we outline here. The f of ui star vi star is really f of x, y, z, x being a function of ui, vi, y being a function of ui and vi, z being a function of ui and vi. And that's what we have here. Okay, this is our function from here to here. Then I went to an etc. because we didn't have time to do any more. There it is. Now, if this function is the gradient of vector field is conservative function, so certain things are going to happen. And what your calculation through this surface would just be the flux of that vector field. If it was a closed surface, the flux of that vector field could be calculated from doing the divergence. You can calculate the divergence of this, integrate over the interior of the region, or from doing a surface interval. Now, the surface that we have here is not closed. It's a cone that's not closed on top. It's truncated on top, but it's not closed. To do a closed cone, you'd actually have to do two integrals. One integral would be over the sloping surface of the cone. Then another integral would be over the surface up here in the plane z equals 6. Well, that wouldn't be difficult. Okay, we could easily calculate the flux of this field through this part of the cone also. And we could calculate it, we could set up the integral of the divergence of this thing over the interior of the cone in rectangular, spherical, or cylindrical coordinates. I wouldn't recommend spherical because the top isn't rounded. Cylindrical or rectangular coordinates, we could do the volume integral. That'd be a straightforward integral. We might go ahead and do that. I'm pretty much done for the day, as you can probably tell. What else can I say about it? Okay, we could have calculated this vector field as a cross product of, as a curl of a vector field. Okay, so if this field is a curl of another vector field, I'm sorry, we could have calculated for any vector field. We could have calculated the curl of this field. Now, if we calculate the curl of this field being a conservative field, the gradient of a scalar function, we know that the curl of that field is 0, so there'd be no point in calculating the curl. But if we did have a field that had a non-zero curl, there'd be a point to applying Stokes' theorem and integrating over, let's just say, this part of the region, the slope part of the cone is bounded by this circle. So we could relate the integral of the curl, the normal component of the curl of this thing, an f dot n, but instead of an f, it'd be a del cross f dot n over the surface. Everything would look a lot the same as this, except our expressions would be different because we'd be doing a curl instead of just a field. But if we replace f by a del cross f, we would have the integral of the curl over this surface, not including the top. Okay, that surface is bounded by the circle, and the integral of the normal component of the curl would have to equal the line integral of the field itself around the circle, and that's Stokes' theorem. And so this kind of an integral can appear in the verification of Stokes' theorem as well as in the verification of the divergence theorem. We're going to do a couple of examples of that. I hope we can get to it. I hope I can get to it in classes a little bit. We still want to do this because people have a lot of trouble with this. We have a fair amount of trouble with surface integrals and line integrals, as well as volume integrals. We need all of these for the big integral theorems. So I had a train of thought and lost it. Let's see, what was I going to say? Well, I don't want to. Yeah, I'm going to pause this and see if I remember what I was going to say. Well, I guess really what needs to be said is simply that, let's see if we're in focus. Yeah. What needs to be said is simply that we need to be able to do volume integrals and flux integrals for the divergence theorem. And we need to be able to do line integrals and surface integrals for Stokes' theorem. And when we do examples of divergence in Stokes' theorem, we're not going to be dealing with functions quite this complicated. But I wanted to relate the actual nuts and bolts of the process and the notations that I used in our briefer summary. The brief summary is to point you toward these things and give you kind of a framework within which to